So let's continue with our discussion on information theory and statistical inference. And we wanted to understand how much information does a random variable y reveal about another random variable x. And we came up with this very interesting toy example, namely the coin toss problem, where we wanted to understand how much information does the outcome of this experiment, the number of heads in the coin toss, how much information does it reveal about the bias of the coin. So the unknown here, the unknown x, is the bias of the coin, and the observed value or variable is the number of heads that you see in n coin tosses. In particular, we wanted to understand how much information is revealed by one coin toss. So every coin toss, how much information does it reveal about the unknown bias of the coin? All right, that's what we wanted to understand. So remember that we observe independent tosses of a coin. Okay, that's our assumption here. The coin tosses that we observe are independent. So suppose that we observe independent coin tosses of a coin with bias half or epsilon, half plus epsilon. So sorry, bias 0 or epsilon. So bias is a difference from half. The probability of showing heads minus half is sometimes called bias, but sometimes as an abuse of notation we just call this half as bias. So this is the unbiased coin which shows which shows heads or tails with equal probability, heads and tails with equal probability, and this is the one which has slightly higher probability of showing heads, half plus epsilon. And we assume a Bayesian setup where a uniform prior is there on two coins. So there are two kind of coins, this one or this one. One of them is chosen with equal probability, and then you toss the coin multiple times independently. The question we are trying to answer is how much information about this bias does each coin toss reveal? So in our language, this x is a uniform random variable. So this x is a uniform random variable showing 0 or 1 with equal probability. And given x, this y is Bernoulli px. Okay, so where p of 0 is, so Bernoulli p of x, this is p subscript x. P of 0 is half and p of 1 is half plus epsilon. So what is the initial uncertainty of x? What is the initial uncertainty of x? Well, that's just the entropy, right? A measure of entropy, uncertainty is entropy. So the initial uncertainty of x is entropy of x, 1, because it can be 0 or 1 with equal probability. So you can show that the entropy is 1. So now the question is, how much is this uncertainty reduced by when we toss the coin multiple times? Okay, when we toss the coin once, let's say. In particular, how much information is revealed, because reduction in uncertainty is information, per coin toss. That's what you want to understand. So there are various ways to formulate and answer this question. The first one answer to this question can be seen from the following formula, which we have been seeing again and again in this course. It's some important formula you should remember. That for uniform prior, the minimum probability of error that you can attain is half into 1 minus total variation distance. And what we can try to understand is how fast does this total variation distance go to 0? How much does this total variation distance reduce by per coin toss? And that will give us some estimate of how much information we get per coin toss. Okay, so so specifically we want to understand how large is this quantity d, total variation distance between w0n, w1n by n. Remember that d w0 w1 for a single coin toss is exactly equal to half. You can check this, exactly equal to epsilon. So earlier we saw that this total variation distance is subadditive, whereby this distance, this is at most epsilon. And we mentioned that this bound is weak, okay, in the sense that we can improve this bound. And indeed, by this Pinsker's inequality, which we saw towards the end of the previous week, this total variation distance by n, so total variation distance is bounded by some constant times the KL divergence. Okay, so this square root of that. So this guy is less than equal to 1 by n, we just retain, and so this is less than equal to this. So this Pinsker's inequality, just a quick reminder, says that dpq is less than equal to ln2 by 2, the Kullback-Leibler divergence between p and q. Square root of that. dpq square is less than this, right? All right. So so we can substitute this bound here. One great thing about this KL divergence is that it's additive. Not so if you have independent distributions, then the total variation distance between W0n and W1n is exactly n times the total variation distance of each guy, just like square of Euclidean distance. It just add the cross coordinates for independent measures. Okay, so this n comes out. So what happens here is, so what happens now? So you have this n 1 by n here, and then you have the square root n factor here, and this we also checked that the divergence between W0 and W1 is equal to log 1 by 1 minus epsilon square. Okay, which is approximately, this guy is approximately epsilon square. So the conclusion is that in fact this thing is not just epsilon, it's epsilon by root n when epsilon is small because of this approximation, but it's epsilon by root n, much smaller than what we thought. Our previous estimate for this was epsilon. So by this refined calculations, firstly two things come out of this calculation. First, very important point, that a question, a philosophical sounding question about how much information is revealed by one coin toss can be converted into a mathematical calculation like this. Second point is that this interplay of distances is very important here. Switching to KL divergence helped us give a better estimate for how much information is revealed by one coin toss. Earlier we were thinking it's epsilon, but now we have refined our estimate to 1 epsilon by root n. And in fact, this estimate is pretty tight. So here is a heuristic statement then. The information revealed, I've not defined information, this is still building heuristics. Information revealed per coin toss is much smaller than what was suggested by our earlier bound. It was saying epsilon, now we have said that it's epsilon by root n. In particular, we need roughly these many coin tosses to get a probability of error of say 1/3. How did we get that estimate? This again, so we have a bound for distance, okay, but this bound for distance can be plugged in here. An upper bound for distance is a lower bound on probability of error, and if you want the probability of error to be less than 1/3, that tells you that the distance must be greater than a constant. So your goal is to ensure that this distance is greater than a constant. But what will it take to make this distance greater than a constant? Well, it will take n to be larger than 1 by epsilon square. Okay, so this gives us an idea of how much information is revealed per coin toss, and using this quantitative measure of this information per coin toss, we can come up with an exact number of how many coin tosses are needed to actually resolve this information. Is the bias half? Resolve this unknown. Is the bias half or half plus epsilon? So we started with entropy of 1. We wanted to make this entropy very small. And what this estimate tells us is that unless you have 1 by epsilon square tosses, you cannot do it. Okay. So this notion of information that we presented in this example is not very formal. It's a little bit informal, but it gives us an idea of how DPQ better captures information than total variation distance. So KL divergence, in some sense, in many examples like this, is a better way of handling information per independent sample than total variation distance. Right? So we'll continue building our heuristic for information revealed about X by Y. See you in the next lecture.